Okay, continuing from where we stopped in the earlier video. So this problem you can solve on your own. Given the value of A, you can find out the eigenvalues and then the eigenvector by following the same process, whatever we have done till now. Then we'll go for the next topic. So the solution of AX involves the following steps, which we already considered. Compute the determinant of A minus lambda I, find the roots of this polynomial, and for each eigenvalue, that means from this roots of the polynomial itself correspond to eigenvalue. For each eigenvalue, solve the equation and find the eigenvectors. So the key equation was Ax equal to lambda x. Most vectors x will not satisfy such an equation. They change direction when multiplied by a, so that ax is not a multiple of x, but we are interested only in those of the special numbers which are in the same direction, which don't change the direction, which are parallel to it. Okay, and those are the special numbers which are known as the eigenvalues, and corresponding to those we also have the special vectors x which correspond to the eigenvectors. So let us take some of the more examples over here. If we take a diagonal matrix which is 3002, which naturally has a lambda 1 equal to 3, which will be same as this, because here we'll have 3 minus lambda, here we'll have 2 minus lambda if I take a minus lambda I, and because the only diagonal elements are there, and this is not there over here, then the natural value will be only the diagonals getting multiplied, and that will give us the roots of the equation to just correspond to lambda I1 equal to 3 and lambda 2 equal to 2, which will be the eigenvalues. Now, corresponding to each one of those eigenvalues, you can find out the eigenvectors by again the Gauss elimination method, which is not shown here, but otherwise you can try. But otherwise also you can just see that because this corresponds to 3, if I take out 3 from the first column, then I'll be left with 1 0. Similarly, if I take out 2 from the second column, I'll be left with 0 1. That's why this will be 0 1. That's another way of dealing with it. On each of the eigenvector A acts like a multiple of the identity. That is, you can just write ax1 is equal to lambda 1 x1, lambda 1 is 3, ax2 is equal to lambda 2 x2, that is lambda 2 is equal to 2. Other vectors, if we have x equal to 1 comma 5, are matrices x1 plus 5x2 of the two eigenvectors, then A multiplies x and x2 is and x2, and it produces the eigenvalues lambda 1 equal to 3 and lambda 2 equal to 2. What it means is, if you multiply A with the value x1 plus 5x2, you're going to get 3x1 plus 10x2, that is 310. Indirectly, what we are talking about is just this. If you have 3002 and then 15 over here, you are going to get 310 over here. Of course, you can just directly use this over here. That means this 1 can be multiplied by 3 and hence we get 3. 5 can be multiplied by 2 and hence we get 10. Okay, so this multiplied by this will give you this value. Then we take another example where we consider the projection matrix, and the projection matrix is this. So half, 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 half. So this will be, again, if you write P minus lambda I, P is now A. So we'll get A minus lambda I as P minus lambda I. That will be half of half minus lambda over here. This will become half minus lambda. This will be half only. This will be half only, and this will be half minus lambda. So if you take the determinant of that, then you are going to get the roots of the determinant to just correspond to lambda 1 equal to 1 and lambda 2 equal to 0. So for lambda 1 equal to 1, then the x1 will be 1 1, and for lambda 2 equal to 0, the x2 value will be equal to 1 by 1 and minus 1, right? So having found this value again by Gauss elimination method, then we have lambda equal to 1 when x projects to itself, lambda equal to 1 when x projects to itself, because each of this is a multiple of this. Each of the column here is a multiple of this, so it's in the same direction as p. X1 is in the same direction as p. And lambda equal to 0 when x projects to a 0 vector. Lambda equal to 0 when x projects to a 0 vector. The column space of P is filled with eigenvectors, and so is the null space. You can see that the column space of this will correspond to the eigenvectors only, and the null space will correspond to the what you call again eigenvectors. So if those spaces have dimensions r and n minus r, then if you take a general matrix, this is a 2 by 2 P we have taken. You can take more ordered P also. Then lambda equal to 1 is repeated r times, and lambda equal to 0 is repeated n minus r times. For example, if you have a projection matrix, something like this, then lambda is equal to 1, 1, 0, 0. 1, 1 is a repeated root, and also 0, 0 is a repeated root. So we'll have the L equal to 0 repeated n minus r times, and L equal to lambda equal to 1 repeated r times. So a 0 eigenvalue signifies that the matrix is singular. Similarly, we can take another example over here. The eigenvalues are on the main diagonal when A is triangular. So if it's triangular, upper triangular or lower triangular, you will have the 3 diagonals. If you multiply, okay, that becomes the determinant, because 0 minus 4, 0 into 4 will be 0, 0 into 5 will be 0, 0 into 6 will be 0. So therefore, we'll get only the diagonal elements multiplied will give us the determinant. So the determinant is just the product of the diagonal entries. In case of a triangular matrix, the determinant is just the product of the diagonal entries. It is 0 if lambda equal to 1, lambda equal to 3 by 4, or lambda equal to half. So that is what it means when we talk about the singularity and diagonal. Then if the value will be 0 if lambda is equal to 1, or lambda equal to 3 by 4, or lambda equal to 1 by 2. So the eigenvalues are already sitting along the main diagonals. So whatever we have here, the eigenvalues are already there here. 1, 3 by 4, and half. Sum of the n eigenvalues equal the sum of the n diagonal entries. That's another thing which we'll have. The sum of the n eigenvalues equal the sum of the n diagonal entries which are there. So the trace of A is lambda 1 plus dot 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 lambda n is equal to A11 plus dot 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 an. Furthermore, the product of n eigenvalues equal the determinant of A. So sum of the eigenvalues will be just the sum of the n diagonal entries. And also, the product of the eigenvalues equals the determinant of A. For a 2 by 2 matrix, the trace and determinant tell us everything, all the information. So if we have something like this, A, B, C, D has a trace A plus D and determinant A, B, D, B, C, then this value, determinant of A minus lambda I, will be determinant of this, and that is equal to, we can just try to write here, lambda square plus A plus D lambda, trace of the value, plus multiplied by lambda, plus the determinant of the whatever is there. So A plus dx plus AD minus BC. Similarly, the eigenvalues can be found from the roots of the quadratic equation over here, and that will become the solution. Thank you.